Good evening, students. My name is Declan. I'm a science teacher here at TUE. Welcome to our live GCSE revision session dedicated to helping you excel in your physics exam tomorrow. This evening, we're diving into effective study techniques, key insights designed to boost your confidence as you prepare for your exams tomorrow. And joining me this evening is...
Hi, my name is Sarah. I'm a science teacher at TUE, and I will be answering your last-minute questions. Please submit your questions through the link I'm going to provide in the chat, where you'll also have some exam-specific tips directly in the YouTube chat. Okay, so good luck. Bye.
Well, thank you very much, Sarah. So what we're going to start off with, we're starting off with our learning objective for this evening's session. And our learning objective is, what do you need to do to prepare for your physics paper 1? So we're going to look into, it breaks it down into 3 learning outcomes for us this evening. Our first one that we're going to look at, we're going to explain how to best tackle different questions on physics paper 1. We're then going to describe a relaxation technique or 2 that can support you during your exams. And then we're going to have a look at the structure of the paper. So what you'll be presented with when you get that paper tomorrow. So we're going to go through some questions. Our first question is going to be on energy. And we're opening our paper up. We're looking at our first question on energy. We've been given a picture which showing us a lift being raised by a crane. And our first question is asking us to describe the energy transfers that take place. 2 marks. Our first strategy that I want to kind of introduce you to, if you've been to any of our live sessions before, you might have come across this. It's called bug. And we're going to box, underline, and glance. So we're going to box our keyword, our command word, so we know what we're having to do. So this one we're going to have to describe. Then we're going to underline any key information. So we're going to underline any key parts to the question. So any keywords, any information, any numbers. I always think numbers, underline them as soon as you see them. So my keywords here are energy transfers. It's telling me energy transfers. So I know I'm doing more than one energy transfer. And then we need to glance at our marks. So have a little look, 2 marks. So we're after probably about 2 things, just to remind ourselves. So what I'd be doing then, I'd be thinking, right, the picture shows a lift being raised by a crane. So we need to describe the energy transfers. So looking at more than one energy transfer. I'd make it really, really simple for myself. So how is this crane being lifted up? So it's being lifted up by an engine. So we've got, in that engine, we've probably got some chemical energy. So we've got some chemical energy in the engine in a fuel. That chemical energy is then getting converted into the movement, lifting that crane up into some kinetic energy. So I would always draw a little diagram just to help me. And then as it's going upwards, that kinetic energy is then getting turned into gravitational potential energy. Gravitational potential energy. So we then want to try and turn this into our answer. So best place to start is always at the beginning. So the first energy transfer. So the chemical energy store of the fuel in the crane is reduced. So it's going down as it's being transferred to the kinetic energy of the lift. So making sure you're mentioning that it's being reduced, because we know that one's going down and the kinetic energy is increasing. Then our next energy transfer was turning that kinetic energy into that gravitational potential energy. So we've made 2 points here. So the kinetic energy is then transferred to the gravitational energy of the lift. So we've made our 2 points for our 2 marks. Make sure you're making enough points for your marks. So we've used our bug strategy to help us there. Our next question. So we're still looking at this same crane. We've got a lift and its contents that have a combined mass of 780 kilograms. The crane raises the lift from 5 meters to 15 meters above the ground. Use the physics equation sheet to choose the equation that allows you to calculate the gravitational potential energy gained by the lift if the gravitational field strength is 9.8 newtons per kilogram. So my first thing that I would do when I see this question, I would underline any important information. So any numbers, just like I said before, so we've got a mass, I've underlined it. We've got a lift, so we know we've got a change in height, and we're going to have to work out our change in height there between 5 and 15. How much is that changed? It's given us 2 heights. We're going to have to make sure we do that. And then we've got our gravitational field strength as well, G. So we can use this information to try and help us find the correct equation. Lucky for you guys, this year, you get given the equation sheet. So we're going to look at the equation sheet to make sure to find our equation. And we're going to set our answer out using this acronym here, FIFA, I like to call it, where we always start off with writing down the formula. We insert our numbers, we fine tune, and then we make sure we write down our answer with our units. So to start off with, we need to find our formula. So we're going to flick to the equation sheet. We're going to have a look at our equation sheet. So our equation sheet looks like this. It's 2 pages. It'll be back to back. Make sure you pull that out of your exam paper and have it next to you so you can see it. So at every question, you can glance at this and go, right, I know what I'm doing. I've got this. It's here to help you. Make sure you're using it. By the end of your exam, you will probably, hopefully, have little scribbles all over it. I'd be tempted when I get it to just write down FIFA to help me remember, oh, FIFA, formula, insert the numbers, fine tune, and then write the answer. I'm writing that at the top of there just to remind us how to do it. So then what we want to do, we want to scan, have a look for our correct equation for gravitational potential energy. So we're having a look, we're looking at the first page, looking if we can spot it. Having a look on the second page. When I spot it, I like to put either a little star or a mark or something. On here, I've circled it, so I know I've used it. So I know where it is, I can see it, and then when I'm copying it from that equation sheet to my right and into my exam paper, I can quite easily do that. So I can see this and I don't get confused with one of the other ones. So this is the kind of scribbles that you should be getting on that equation sheet. So my first job, after I like to write formula, insert numbers, fine tune, and answer, I like to write that in like the margin or the side of the paper. You could even, in the side of the answer spot, you could even just write FIFA if it helps you. If it helps you remember a way to work that out. So the first thing we do, writing down that formula. Make sure you write the formula. That could get you 1 easy mark. 1 easy mark just for writing something from that equation sheet in the correct question. A really nice mark, nice confidence boost. Then our next job is inserting our numbers. So we insert our numbers into the equation. So we've got our mass, which we've got in the question, 780 kilograms. We've got our gravitational field strength, 9.8, which we've written in. And then we've got our height. We know we have to work out the change in height. So to work out the change, we've looked at our end height, take away our start height. So 15, take away 5. So 15 minus 5. Next, we might want to do some fine tuning. So here I can see a few bits of fine tuning that I would want to do to make this easy for me to type into my calculator. So fine tuning is our next step. So I've made it simpler for myself. I've done my 15 minus 5, which is 10. And then I've also done my 780 multiplied by 9.8 and worked that out to be 7,644. And then it gives me just 2 numbers to type into my calculator. Don't type anything into your calculator until you've got things written down on your page, because then you can see, right, I've written it. It's exactly what I've written in my calculator that's written down on my page. And then we write down our answer. So FIFA, the last step is our answer. So the gravitational potential energy is 76,440 joules. It's an energy, so we know it's measured in joules. You may get a mark for the answer, for the units. People love to see units. So 76,440 joules. And that would get us a full marks for that question. So remember to use that FIFA whenever you see a maths, a calculation question in physics or in science or anywhere. Use that FIFA method to help you. You clearly sets the working out. So we've got another question here. Still looking at this crane. So the chemical energy input as fuel into the crane was 240,000 joules. Use your answer for the gravitational potential energy gained by the lift and the equation from the physics equation sheet to calculate the percentage efficiency of the crane. So straight away, I do the same thing again. I write FIFA at the side of my question to help me, to remind me what to do. It's just something that helps me, reminds me what to do. So first job I need to do is find that formula. I know I've got an energy that's been going in there, and I know I've got my gravitational potential energy from the question before. Then we need to go to our equation sheet. So our best friend for this exam. If you're not flicking to and from this equation sheet all the time, then you might be missing valuable marks, easy marks. So we're looking for efficiency. So we're looking for energy efficiency as well, because we're talking about energy. So having a look, did you spot it? So it's there. Once again, I've circled it. You might put a little dash, a star, something next to it. If you've got a highlighter, you could highlight it. You've got all those options. And it makes it dead easy for you to spot, right, it's that equation now. I'm using this one. So we've got two efficiency equations. So one's finding out the energy efficiency, and one's finding out the power efficiency. But they're very similar equations. It's always the useful divided by the total going in. So very similar equations. So my first step, as I said before, in our FIFA method, is going to be writing down that equation. So efficiency equals our useful energy divided by our total energy. So writing that equation down, making sure it's there. Our next step, inserting those numbers, making sure you put the correct numbers in. So inserting those numbers, so efficiency. So we've got our useful energy, our gravitational potential energy from the question before, our GPE, which is that 76,440 joules, divided by the total amount that went in. So divided by the total amount that went in, and I've got that from up here in the question. So I've got that from up here. It told me the chemical energy input as fuel into the crane was this much, and I've put that there. Then our next step is doing some fine tuning. So it's asked for percentage efficiency. We've now worked out the efficiency. So my efficiency here is 0.32. If you get a number bigger than 1, you've done something wrong. So if you've got a number bigger than 1, next little trick that you can try is just flipping those numbers around. So maybe you've done your divide the wrong way around. Try flipping them around. You should get a decimal at this stage. But it wants it in a percentage. So we now need to turn this decimal into a percentage. So we're going to turn that decimal into percentage by multiplying it by 100 to get it as a percentage efficiency. So 0.32 multiplied by 100. And that will give us our answer, which is 32%. And using that FIFA method, we've made it really, really clear on exactly what we've done step by step. So we've done everything step by step, made it really, really clear, really simple for the examiner to actually see what we've done, how we've done it. And that's how we get all 3 marks, making it dead obvious with what we do. Moving on to this question about the crane. So talking about the efficiency a bit more. So the crane has not been serviced in a long time. Why might that impact the energy efficiency of the crane? So thinking about service, my car, you need to go service your car. When you service your car, they change the oil, they put new oil in, makes all those parts lubricated, makes them move easier, stops energy being wasted. So we've got 2 marks. So we need to bug, remember? So we need to be looking at how many marks we've got for this question. So making sure you answer your answer provides all details to secure the marks. We're looking for at least 2 points here. At least 2 points for how might the efficiency be impacted. So my first thing, I'd be saying, right, if it's not been serviced, it's not going to be as efficient. So straight away, I will go, the efficiency of the crane will be lower. It might be dead obvious to you, but make sure the examiner knows that you know that. The efficiency of the crane will be lower. Straight away, in there with the key detail. Then, why will it be lower? So why will it be lower? It's because a lower proportion of that chemical energy that's going in will be converted into that useful kinetic energy to move the crane higher. So it's not as efficient, not as much energy is being used for the useful purpose. And then you may want to expand and say where that energy is going. If it's not going into the crane, where is it going? So you might want to say some of it could be lost as heat or sound. Those parts getting really hot because they're not lubricated. It could be that it's giving off more sound. It's making noises because it's not. It's losing that energy. So that would get us the 2 marks. We made 3 points, which is more than enough information. Another question about our crane. So we're still looking at energy here. So a fault causes the crane with a mass of 780 kilograms to break and the lift falls 15 meters to the ground. Use the gravitational potential energy of the lift and the equation from the physics equation sheet to calculate the maximum speed the lift reaches before it hits the ground. So we know we're going to be having to do some calculating here. So once again, we're going to use the FIFA method to help us set this out. But we're going to do something that I like to call the old FIFA 1-2. So first off, underlining all our information so we know what we've got, we know what we're looking for. And we know in this question, we're talking about kinetic energy because we're talking about movement, and we're talking about gravitational potential energy lost, and they're being equal because of conservation of energy. So the kinetic energy gained is going to be equal to the amount of gravitational potential energy that gets lost. So we need to do the old phi for 1, 2. So we're going to have to work out our gravitational potential energy. We're going to have to work out our velocity or our speed. So I like to write phi for 1, phi for 2. If it's got lots of room for this question, I'd be tempted to draw a line down the middle so I can split my 2 bits. So then I would write down what I'm actually working out at each side so I don't get confused. So it's dead clear to me what I'm doing. So phi for 1, we're working out the gravitational potential energy. Phi for 2, we're working out our velocity. My next step, I would F for FIFA. So we want to go to our equation, F for formula. So we want to go to our equation sheet. Find our formulas for each of these equations. So we want to find the one for gravitational potential energy. We want to find the one for kinetic energy because these are linked. So we're having a look around. We might have already circled our gravitational potential energy one. And normally, all our similar equations are in similar places. So you'll see all the energy equations are close together. All the ones about electricity are close together. The two efficiency equations next to each other. So having a look for those correct equations, kinetic energy, gravitational potential energy. There they were. They were some of the first ones on that sheet. So some of the first ones on our equation sheet. And I've circled them to make sure I can spot them. So we've got them there. Our kinetic energy equals, and then we write them down. So we're going to write them down into our formula section for each box. So our first one, our phi for 1, we know how to work out our gravitational potential energy. And our phi for 2, we know how to work out the kinetic energy to get the velocity. That's our end goal here, that velocity. So looking next, our next step, we want to do our first equation. So our first equation, we want to insert our numbers. So inserting our numbers, we've got 780 because that's the mass of the crane that we've got from the question up there. 9.8 from that earlier question where it was telling us the gravitational field strength. We probably know it by now. And then 15 because that's how far it's fallen. We could then quite easily type this into our calculator to get our answer, which skips for us. We don't need to do the fine tuning step for this question, for this side, because there's no real fine tuning. We can type that into our calculator. As long as we've typed it correctly, we get the correct answer, which is 114,660 joules. Remember, energy. So we're talking about energy and conservation of energy. So we're talking in energy now. Then we go to our phi for 2. So our kinetic energy. So we're going to use this number. That's going to be our kinetic energy. So we're going to put this number into this equation. So our next job over there is inserting our numbers. So we've inserted that number, we've pulled it from over there. We've got our half or 0.5, whichever one you prefer to write it as, 780, which is the mass, and then we're trying to work out the velocity, and velocity is currently v squared. Our next job is doing some fine tuning in this one so we can get v on its own. So moving it around a little, we get v squared equals there. So we've rearranged our equation. So use that fine tuning for rearranging, dealing with units, working out little multiplications you can, working out what v squared would be. So v squared equals 294. But it didn't ask us for v squared. It's asked us for the maximum speed. So we now need to find the square root of that answer, which is going to be 17 meters per second. So we've done our old phi for 1, 2 to make sure we've got all our working and it's really clear for us. So some top tips for tomorrow. So make sure you read the question so you're really, really clear on what is being asked of you. Make sure in any calculations you follow that FIFA method to work out to get all those marks that you can possibly get. And then number 3, remember to work out change in a variable. So where we looked at height change there, people often miss that and they might just put 15 or 5. They wouldn't have got 10. So make sure, check. If it's giving you two heights, look at that height change or temperature change, normally common ones. And then make sure your answer provides all the detail to secure your marks. If it's 2 marks, make sure you've got at least 2 points. If it's 6 marks, make sure you're looking at 6 points. So now we're going to move on to a question about electricity. So electricity, this diagram is showing us a really simple circuit. What I would do straight away, I'd go, right, what type of circuit have I got? I've got a parallel circuit. So I've got the two loops. I know it's a parallel circuit because I've got those two loops that never touch, like train tracks, never touching, and they're parallel. So it helps me. I'd be tempted to write that somewhere on here, just to remind me, parallel. And then we read the question. So a battery has three identical cells. So we're looking for three cells. If we weren't sure what they are, we've got these, we've got three of up here. Each cell has a potential difference of 2 volts. What I would do is I would write 2 volts, 2 volts, 2 volts, just to remind myself, oh, I've got the three identical cells here, 2 volts, 2 volts, 2 volts. What is the potential difference of the battery? So how are we going to find that? Oh, I've got 2 volts, I've got 2 volts, I've got 2 volts. So the battery is all the cells put together. So we're just going to add those, and it's going to be 6 volts. As well as writing it in the answer box, I would make sure to write it on the circuit as well. Whatever information you work out about this circuit, you put it on the question as well, on the diagram. It's like a puzzle, electricity. It's just solving all those little bits, making sure it all fits, making sure it all works out. So we've got that little 6 volts up here now to remind us that we've got 6 volts. So next job, we're going to state the reading on the voltmeter, and it's 1 mark. State, we're not having to do much. It's a 1 mark. We're not having to do much. So first off, let's find the voltmeter. So the voltmeter, the circle with the V in, helps us remember it's a voltmeter. And then we're not having to do much. So where else have we got a reading for voltage or potential difference? Oh, up here on the battery. So now we're thinking, right, how do these link? So we're thinking, how do these link? We might think, so it's asking us to state. It's not asking us for anything too challenging. So it's 1 mark, asking us to state. So the answer would be 6 volts because it's the same reading. The reason for that is because we've got a parallel circuit. The voltage, the potential difference is the same across each branch. So this resistor, this branch here, will have 6 volts on. This will have 6 volts. So we've got 6 volts on each branch. The potential difference is the same all the way around the circuit. But because it was a state, we know we were being asked to do something quite easy. And then once again, I've written it down here to remind me. So I don't forget, oh, 6 volts, should remember that one. Now we've got another question about this circuit. So the current through the 2 ohm resistor is 3 amps. The current through the bulb is 1.5 amps. What is the reading on the ammeter A1? 2 marks. Sometimes they like to give us bits of information that aren't relevant to what we're doing. It might be relevant later on, but it's not relevant to start with. So this question's done exactly that. The current through the 2 ohm resistor is 3 amps. We don't need to know its resistance right now because we're looking for current. We're looking for the current on this first ammeter here. And it's 2 marks, so we know we're going to have to do something to get these 2 marks. So we're going to have to do a little bit more than just picking a number off this circuit. What I like to do, I like to add an ammeter in the exact opposite place as well, just to remind me. So just to remind me that these should be the same. And that will be the total current for this circuit. So we're looking at it, we've got these branches here where the bit of the circuit breaks off. And the current is flowing through. And at this section, it divides, it splits between the 2 branches. So we've got 3 amps and we've got 1.5 amps. And then at the branch, it comes back together. So to complete this, we just need to do 3 and 1.5 because it's split at this branch. When it comes back together, we've got our total current. So before it's split, we know we've got 3 amps add 1.5. So our 3 add 1.5, which is going to be 4.5. And then I would make sure I write it on the circuit as well. Write it on the circuit. I'd write it on my ammeter that I penciled in over there just to refresh myself, just so I don't forget. So look, we're filling in the gaps. It's like a filling in the gaps game in electricity, working out what's missing. So next, we've got a nice one here. So look, it's 1 mark, a quick multiple choice. So use the correct answer from below to complete the sentence about the bulb. So the bulb has a resistance blank 2 ohms. And then we've got 3 options: less than, equal to, or greater than. So remember to answer all multiple choice questions. If you're given multiple choice questions on that exam paper, make sure you're attempting them because you could be throwing away valuable, quite easy marks. Even if you take a guess, it's a 1 in 3 chance, isn't it, that you're going to get it correct. So let's have a look. The bulb has a resistance, something, 2 ohms. We can work this out by looking at the current. Current, it's like us, it's lazy. It likes to go the easiest path. So more current will go the easier path, the path of the least resistance. So we can see there's more current on this top path than the bottom path. So that means this top path has got less resistance. So we know the bulb has a greater than 2 ohms resistance. So we know it's got a bigger resistance because it's got less current. Because current, like us, it's lazy, it likes to go the easiest route. Likes to go that easy route, likes to make sure it's easy, the easiest way, the path of the least resistance. So more current, less resistance. Less current, more resistance. Sometimes they might ask you why. We went into a little bit of detail there about it, about the current wanting to go. I can see because it's got more current there, so it's got less resistance. Or you could say the opposite. Sometimes they might ask you to prove it. So sometimes they might ask you to prove it with a little calculation. And you know us physicists, we love doing calculations. We love you doing calculations. And whenever I see calculate, I go, you know where I want to visit? I want to visit FIFA again. I want to get my FIFA in there, and I need to visit my equation sheet. If I ever see calculate, I know I'm writing FIFA in the margin, at the side, wherever I can write it, and then I'm visiting my equation sheet. So we're looking now. So we're looking for something that's going to find us the resistance of that bulb. We've got a potential difference, and we've got a current. So we're looking for something that's going to be linked resistance, potential difference, and current. So let's have a look at our equation sheet, see if we can spot it. So we're looking for an equation on there that links those three things: resistance, potential difference, and current. See if you can spot it. So that's one page, then we've got our next page. And there it is. Once again, I've circled it to make it dead easy for me to spot. Because us physicists are lazy, we don't like to write the whole thing out every time. We can just write V equals IR when we get back to our question. So our formula for this, V equals IR. Potential difference equals current multiplied by resistance, to remind us. Then we insert our numbers. So inserting the numbers, F, I, insert the numbers. So we know our potential difference. We pulled it from over here, that's 6. We've got our 1.5 that we've got from the ammeter reading there. So that's where that information's come from. Then, next bit, we're going to have to do some fine tuning because we're actually after resistance. So we need to do some rearranging of this equation to find resistance. So resistance equals 6 divided by 1.5. Then, and only then, do you do any typing into that calculator. So typing this into your calculator, and that gets you your answer of 4 ohms, which has proved what we said earlier. The bulb's got a bigger resistance than that. So the bulb's got a much, much bigger resistance than that 2 ohms there, than the 2 ohm resistor. So we've proved what we said using some maths. Next, it's asking us to draw a diagram to show a circuit. It's asking us to draw the diagram to show a circuit you would use to obtain an IV characteristic of a component in a circuit. So our first thing we want to do, we think, right, it's asking us to draw a diagram. So we know circuit diagram, right, get my ruler out. What components can I remember? It's asking us to do an IV. If you can't remember, I, current, V, potential difference. And when it's wanting to find the characteristics, we're going to then plot it into a graph. So it's the information that we need to be thinking about. What I like to do when I approach these, I like to make sure I draw all my circuit symbols. So I draw all my circuit symbols that I'm going to use, and I can cross them off as I go through. You might get given pictures of the equipment and say, use this, or finish this circuit. There's lots of variations of this question. This is one of the required practicals, so it's helpful to be familiar with the methods for them. And I know that Sarah will be sharing them in chat at some point. So we know for our circuit, we need a battery. We need a power supply. So I'd always draw a battery. You could use a cell. You could use a variable power supply, whichever one you can remember. Then we know we'll need to find the current. So to find the current, I'm going to need an ammeter. So I would make sure I make a note. I'm remembering my symbols now. Right, ammeter. What do I need next? I need something to measure the potential difference. So a circle with a V and my voltmeter. It doesn't tell us what component. Doesn't tell us what component we're looking at. So I'm just going to put a box that says component. In your exam, this could be a bulb, which would be your circle with your cross. It could be a resistor, which would just be this box without the word component, or it could be a diode, and we've got a diode symbol shortly, where it's the symbol that looks like this. So it could be a diode, remembering that diodes only go one way. And then we need to be able to alter our current so we can record the voltage. And we're going to use a variable resistor for that. So we've got our variable resistor. So now the next step is linking all these up, is connecting them up into a circuit. And that's what I would do below. So below this, after I've identified what I want to use, my equipment, I'll then turn it into a complete circuit. So my complete circuit is here. Remembering the ammeter goes in series, so it goes in the same loop as the other components. Remember, series, one after another after another. My favorite way to watch a TV show. One episode, then the next episode, then the next episode. So you've got one component, the next component, the next component, the ammeter in series. And then the voltmeter around the component that you're looking at. So this component here, this is what we're looking at. So we put the voltmeter around it so it can check that change in energy, so that it can work out its potential difference over there. So we've drawn our circuit, and that will be our 3 marks, making sure you've got your ammeter in the right place, your voltmeter in the right place, and the rest of them connected up correctly. Next, of course, it's going to ask us, would you use this circuit to obtain a current voltage characteristic graph for a component in the circuit? That component, it might be a bulb, like I said, it might be a resistor, it could be a diode. They're the 3 that it could be. That could be 3 different things, and be ready to swap that component out for one of those. So what we'd have to do in this question, I would make sure I tell them exactly how I'm doing everything. So setting up the circuit as I've drawn in the diagram. That would be my first point. Set up the circuit as seen in the diagram. Then how are you going to find the current? Find the current by using the ammeter. Find the potential difference by using the voltmeter. Then what are you going to do next? Use the variable resistor to alter the current and record values of the current and the potential difference. So set up the circuit and adjust the variable resistor to vary the current. Record pairs of readings of the current and potential difference from the ammeter and the voltmeter. And then make sure to mention repeats. When in doubt, if you're talking about an experiment, talk about repeats. Make sure you say, repeat this, repeat this, repeat this. And then, because our aim is to plot that graph, I've even remembered to mention, plot the readings obtained on a graph, just to make sure the examiner knows what I'm talking about, knows where my end goal is here. So we've managed to get all our marks there. We've said how we're going to get the current. We've said how we're going to get the potential difference. And then we've said how we're going to change that experiment, what we're going to do with the variable resistor, and what we're going to do with our results. So a lovely method there, a really nice method. Remember, step by step that method. Make it so it's a set of instructions you could follow. Make sure it makes sense when you're writing it. Have a read back. Go, okay, act it out in your head. Close your eyes, act it out. This doesn't make sense. Let's add in a little bit here. Feel free to do that. So as a bit of a refresher, you've got your required practicals for this paper. So your specific heat capacity, your resistance, your current, potential difference characteristics, which we've just looked at, and density. Make sure that you are happy with these, and there should be a link that's been shared in the chat for the different required practicals, so you can open them when you want, and maybe have a look at those tonight. Our next question. Oh, look, we've got the graphs. It could ask you, it could give you some results and say plot a graph, but this time we've got the 3 graphs that we're going to look at. So we've got our 3 different graphs, and we need to match the graphs to the conductors below. 3 marks, 1 mark for each correct match up. Make sure even if you have a go, if you've got no clue, have a go. So it's a multiple choice. So first off, we will want to look at our graphs. Look at the difference between them. So our wire, we know our wire is an ohmic component. It follows Ohm's law, where current and potential difference are directly proportional. If one doubles, so does the other one. So we're looking for a graph where if one of them doubles, so does the other one. So we're looking for a straight line. Which one's our straight line? Yeah, our wire matching up to that last one there. Next, we're looking for filament lamp. So the filament lamp, as it's getting hotter, so as it has more energy is coming through, it's getting hotter, which is increasing the resistance. And increasing the resistance makes it so the current levels off, makes it so not as much current comes through. So our filament lamp matching up over there, matching up to this curly one. And then the diode only works one way. So it's the only one that's not symmetrical. The only one we wouldn't be able to put a mirror in somehow and get that reverse pattern. So the diode is this one in the middle. It has a threshold voltage where suddenly the current's allowed to flow. So the current's allowed to flow at that point. So we managed to match them up. If it helps you, some tips. So the circuit symbol for your wire, if you're drawing a wire in your circuit symbol, it's a straight line. It's a straight line. So look, straight line graph. Or wire and resistor, straight line. Our filament lamp, we could draw a nice curvy F, a really curvy F, and it'll look similar to this, an F, a big curly F to help us remember. And then the diode, it's the only one that's not symmetrical. The only one that's not symmetrical there. So it's just an easy way to help you remember. So some top tips about that section. Remember to answer all your multiple choice questions. Check the values you obtain from your calculations. Be familiar with the methods for required practicals. Be clear on the different IV characteristic graphs. So make sure you're happy with all of those. And then I don't know about you, but after some electricity, I always need to just have a moment of relaxing. So if you're finding yourself in that exam tomorrow, needing a moment of relax, try this method. So you've got your fingers, you've got your hand, and then I'll just run your finger over your hand. So breathing in, and then pull that hand in, breathe out, pulling that finger in. If you're feeling a bit nervous having it in front of you, counting to 5, breathing in and breathing out, just hold it on your leg and breathing in, breathing out. Remember, if you've got really worked up, you've got 10 fingers. 10 fingers. So after some electricity, you might want to use all 10 fingers. You never know. So we're going to move on to our last question of this evening. So all about the particle model of matter. So this picture, it's showing a kettle containing water that's been boiled to make a cup of tea. They like to show us nice little pictures of things that we know to make us think, yeah, I know what I'm talking about here. It's a kettle. So the kettle contains 0.75 kilograms of water. Use an equation from the equation sheet. Yes, my best friend, going back to him again. To calculate the energy required to warm the water from 20 degrees C to 100 degrees C if the specific heat capacity of water is 4,200. So straight away, we can see calculate. Calculate, we know exactly what we're doing here. As we know, we're underlining that information, and then we're using our FIFA method. So FIFA, formula, insert numbers, fine tune, answer to help it so we can set this out, get all those easy marks. So use those variables to help you work out which formula you're going to use. So first off, we're going to find our formula now. So we've wrote formula, we need to go find it. So looking at our best friend again, having a flick through our best friend, looking for that change in thermal energy, remember. So we've got our mass, we've got a change in temperature, we've got a specific heat capacity, and we're after change in energy. So having a quick look. Did you spot it? So like I said, every time, put a circle, put a mark next to it, an arrow. You could even write the question you used it on next to it. That's a good idea. Writing the little question. If it's question 4, put 4, 4A, 4A, something like that. So writing down where you're going to use it. So straight away, write it into the question. So F for formula. Next, we're inserting those numbers. So inserting those numbers into the equation. So 0.75 multiplied by 4,200 multiplied by our change in temperature. Remember, whenever you see this delta sign, it means change in. We've got our equation there written out. Fine-tuning it a little. So I've done my 100 minus 20. I could have done 0.75 multiplied by 4,200 if I wanted to. But whatever makes you feel comfortable. Then the next job, making sure typing it into your calculator to get that answer. Make it as simple as possible to type into that calculator for yourself. So typing it into the calculator to get that answer and then writing that answer down. So the change in energy is 252,000 joules. And we're talking about energy again, so we know it's going to be in joules. So those marks, really, really easy to get if you use the FIFA method. And remember to calculate the change in temperature, how to calculate it, how to calculate the change in temperature, where we've got the end, take away the start. So we've worked out the change in temperature there. Perfect. So we're going to probably be talking about this kettle for a few questions now. So we're still looking at this kettle. So use the particle model of matter to describe how heating a kettle causes the arrangement of water particles to change as the water boils. You should include a description of how the particles are arranged in the liquid water and in the steam produced. So, okay, right. But when we get these big wordy questions, I like to do bug. So boxing that the command words where it's telling me exactly what to do. It's hidden in this one. Underlining any important information, and then glancing, having a glance at those marks. So first off, describing. I'm going to be doing some describing, stating those points, stating information about it. If you were describing me, you'd say he's got a nice beard, he's got some nice glasses, things like that. So you're saying points about it. Next, we're going to be underlining. Underline any things you think are important. So I think dead important, the particles, how are those particles arranged? And how are they arranged in liquid water and in the steam produced? Dead important bits. Then have a little glance at the marks. A glance at the marks, 6 marks. So top tip here, make enough points to secure all the marks in these extended writing questions. So this is a bit of an extended writing question because we're describing 6 marks. It's got lots of information it wants us to say. So what I would do here straight away when I think particle model, so I see particle model up here, I would make sure I draw a picture of the story of what's happening. So in my head, I've got, right, we're going from a liquid. So I've drawn the particles in a liquid. I know we're heating that liquid up. We're heating that liquid up and it's turning into a gas. So it's just giving me this extra little visual cue to help me make sure I get as many marks as possible. Because now I'm just describing a picture. I'm describing what's happening in my picture up here. So starting off by talking about the arrangement of the particles in the water, saying how it's irregular. Look, they're random. They're not in a normal pattern, and the movement is random. There's gaps. They can move around a little bit. So I've spoke about how those particles in the liquid water are arranged. Boom, tick that off as I go. Next, what are we doing next? We're having to heat it. So having to heat it, make sure I say this, what happens? Heating the kettle increases the temperature of the water. So by heating it, it might sound stupidly obvious. Yeah, heating it, it's increasing that temperature. So there, I've got my next mark, my next point. What's that then doing inside the actual liquid? So inside that liquid, thinking about that internal energy, because we're increasing the temperature, the internal energy is also increasing. So that internal energy also increasing. So we're breaking it down into these steps here. By increasing that internal energy, we're increasing the temperature, we're getting it closer to its boiling point. And when this liquid reaches its boiling point, the water particles have got enough internal energy, they're going to move fast enough, they're going to break free of these bonds or forces holding them together. So the bonds or the forces holding them together. I would probably say forces that are holding them together. So the breaking free. And then we've got to describe our particles in the gas. So in our gas, our particles are spread out. So our particles are nice and spread out and they're moving randomly. So we've managed to say 6 points here for our 6 marks. I'd be happy there. I'd look at that, go, yeah, that's good. You can write in bullet points, that's completely fine. As long as it's structured, as long as it's in a logical order, as long as it makes sense. And I think the picture helps me make it make sense. It helped me tell that story a bit like a comic. So making sure you're describing what's happening to the energy, how that energy is changing that liquid into a gas. And now another question about our kettle. So we've got our kettle that's been boiled. Some of the energy supplied causes the water to boil without the temperature of the water increasing. Okay, what is the name given to this energy supplied? So we've got three options: latent heat of freezing, latent heat of fusion, and latent heat of vaporization. Top tip: make sure you read all the answers in your multiple choice before you even think about answering, before you even look at answering that. So first off, we know latent heat of freezing, it's not really relevant to us. It doesn't really exist. But if we're talking about freezing, that straight away makes me think, right, I'm going from a liquid to a solid. We're not. We're not going from a liquid to a solid. We're going from a liquid to a gas. Next, we've got two others left: latent heat of fusion, latent heat of vaporization. One of these straight away is ringing a bell for me, because I'm thinking, right, if we're going from a liquid to a gas, my gaseous water, it's called water vapor. Water vapor. So it's giving me a bit of a hint there. So I know that's why I'm going to tick that one. Water vapor. Fusion is that liquid solid area. That latent heat of fusion going from a solid to a liquid, that area. So we know it's not that one as well. I like to put little crosses, crossing out, ruling out the ones that it can't be until I get to the end product, until I get to my latent heat of vaporization. So that get me my 1 mark. Make sure you read all the answers before you pick one. So little top tips for that section: use variables in the question to identify the correct equation. Make sure you've got enough points to secure all your marks. So in that extended writing, so we did 6 points for 6 marks. Read all the answers in a multiple choice before answering. And make sure you learn the particle theory of matter and how it explains properties of the 3 states of matter and the change of state. Make sure you've got a good idea of that particle theory. So we've gone through some different exam style questions. We've had a go at tackling them. So we've explained how best to tackle them. We've also looked at some different relaxation techniques. A relaxation technique to calm you. If you're getting worked up, if you think you're getting a bit worried in that exam, do that. Now we're just going to have a quick look at the structure of the physics paper. So we're going to have a look at a quick look at the structure of the physics paper, and then we're going to see if we've got some questions as well after that. So our physics paper will look like this. It's going to look like this. We'll see a page that looks like this. Big F up here, F for foundation, and H for higher. Make sure you've got the right paper in front of you. If you're expecting to sit foundation, make sure you've got the foundation paper. Make sure you've got the higher paper. If not, get that hand up. Make sure someone knows. Tell someone. Make sure you know what you're going in for tomorrow. So we're zooming in now a little bit. Things you're going to need for this paper tomorrow: you're going to need a ruler, a calculator, and the physics equation sheet, which should be inside. If when you get to your paper, you have a quick flick through, see if you can find it. Get it out on the desk. If it's not there, put your hand up. Make sure someone knows. Make sure you've got a calculator you're happy with using. If you've had to borrow a calculator, see if they've got one they can lend you. And then make sure you answer all the questions in the space provided. You've got plenty of space in those. Don't go around the edges. There's normally black lines saying do not write in this space. And do everything in this book. Any work you do, get it in there. There's no point doing stuff on a scrap piece of paper that you're going to throw away, because it could have got you a mark. And anything you don't want, just make sure you put a little cross through it as well. It tells you how many marks you've got, and it tells you how many marks you'll get per question. And it even gives you a little bit of advice. In all calculations, show how to clearly work out your answer. How are we going to do that? We're going to do the FIFA method, remember? FIFA. Write that at the top of your equation sheet, FIFA, to help remind you. We're going to do that every maths question. Then we've got where we're going to fill in our information. You should be given this. You will know most of this information at this stage. And then your equation sheet. You're the last year that's going to get it. So the last year that's going to get it. After you guys, the people have got to remember them again. So think yourselves lucky. And then we're looking at the demand of the questions. So the questions, they start off quite easy. So low demand, and then they rise up, get a little bit harder, right, fall back down, harder again, fall back down until they ramp up at the end of the exam. The hardest question will be that last one at the end of the exam for both papers. So don't give up. So if you get to this stage here on this question, go to the next question. See if you can get those easy marks for yourself. Don't doubt yourself. And then, so yeah, we're just talking about those questions. So we've looked at the structure of the physics paper there. So now we've got about 10 minutes where we're going to be able to go through some little bits and bobs, little questions that we might have that people might have filled in on the form. So our learning objective today was, what do you need to do to prepare for your physics paper 1? And now we're going to have a look at some questions that Sarah's been taking for me. So let's have a look. We've got, this is a nice one. What is the difference between a parallel and a series circuit? So what is the difference between a parallel and a series circuit? I'm going to try and use my neatest writing on here to do this. So a series circuit, we always start with our cell. That's an awful drawing of a cell, but we're doing our best. A series circuit will have one component, then the next component, then the next component, and it'll just keep having component after component after component. So here I've used some bulbs, maybe not the neatest. I probably could have used a ruler to have a go. So a series circuit, it will be one loop. Like I say, in the way I remember it, a television series. My favorite way to watch any television series is to watch one episode, then the next episode, then the next episode. You should see me watching Below Deck. One episode of Below Deck, the next episode of Below Deck. I have to know what happens. Will they get the fenders out on time? No one knows. So then we've got one component, the next component, the next component, and it's one singular loop. So there we've got a series circuit. So we've got a series circuit. Now, other type of circuit, a parallel circuit. When I think about parallel, I think about two lines that go here that never touch. Thinking about train tracks. So doing the same in a parallel circuit. So my parallel circuit, how I would draw it, I'd start off and I would draw a series circuit to start with. Oh, well, I'm going to just go back a little. I forgot to add any bulbs in. So I'd start off, I'd draw my first loop. Drawing the first loop. If I was having to put 3 bulbs into parallel, we'd then have the next loop. And then if I was putting another one into parallel, another loop. That's a terrible bulb. So we've got a parallel circuit here. The difference between them, series, one loop, parallel, they're never touching. They're those different branches that aren't touching. They never touch. The current splits. So the difference between them, series circuit, if one of these components breaks, all of them will go out. So all of these will go out if one of them breaks. If we take one bulb out of that circuit, leave a gap, all 3 will go out. In the parallel circuit, if one breaks, the other 2 will stay on. So these are like the light bulbs in your house. These are like the old school fairy lights you might have had, where if one went out, they all went out, and you've got to go around testing everyone. In a series circuit, the current is the same all the way around. Current is constant. And that's constant. Yeah, constant. And that's because it's only got one path it can flow down. It's got that one path. So the current is the same wherever we are. In a parallel circuit, the current is shared between the branches. So the current splits. And that it gets to a junction, and some of it goes this way, some of it keeps going, some of it goes this way, some of it keeps going, some of it goes this way, some of it, and then they all join back up to get our total current back at the end. That's because those charge carriers are choosing different ways to go. In a series circuit, our potential difference is shared between, so if this was 6 volts up here, we'd have 2 volts, 2 volts, 2 volts. So we'd have 2 volts, 2 volts, 2 volts. It's split. It's shared. It's shared or splits. Look at what's happening here. We've got splits, current splits. So in a parallel circuit, the potential difference in a parallel circuit is constant. It's the same across each loop. It's constant. Constant. Look at what's happened. The rules, they've just like flipped really, haven't they? So if this was 6 volts up here, this bulb would be 6 volts. This bulb would be 6 volts. This bulb would be 6 volts. If we had 2 bulbs on one of them, so if we added another bulb into that bottom one, if we had 2 bulbs here, we've got a mini series circuit. So those 6 volts get shared into 3 and 3 volts. So it's this constant across each branch. So that's the difference between a series and a parallel circuit. Well, I'll see what other questions we've got. What question have we got? Difference between alpha, beta, and gamma. That's quite a nice one. We'll see how far we can get with this one. So difference between alpha, beta, and gamma. Can we explain the difference between alpha, beta, and gamma? Perfect. So difference between them, we've got our 3 types of radiation. So we've got our 3 types of radiation. We've got alpha, we've got beta, we've got gamma. Gamma, it's an electromagnetic wave. So it's an electromagnetic wave. Beta, it's a fast-moving electron. A fast-moving electron. Alpha is a helium nuclei, which means it's got 2 protons and 2 neutrons. So it's 2 protons, 2 neutrons. So alpha's the biggest one. So alpha's the biggest one. It's got 2 protons, 2 neutrons, which means it can get stopped the easiest. So it gets stopped the easiest. It can get stopped by a piece of paper. It can get blocked by our absorbed by a piece of paper. So it gets absorbed by. So it can get absorbed by paper. It can get blocked by paper. It can get blocked by skin. It can't pass into our through there. Beta can pass through paper, but it can't pass through a thin piece of aluminium. Thin aluminium. And then the gamma, you need a really, really thick piece of concrete or lead. Thick piece of concrete or lead to stop it. So it's because it's a wave, it's much, much harder to stop. Alpha, because it's got 2 protons, it's got the highest charge, so it's the most ionizing. Ionizing means it's the highest chance of causing damage to one of our cells, creating an ion. So it's creating an ion. So alpha, the most ionizing, whereas gamma, the least ionizing, even though it's passing through our body all the time. So it can pass through our body. It's the least ionizing, so it's the least chance of creating an ion in one of our cells. Beta, the middle one, the moderate, it's middle range. Alpha, the shortest distance in air. Gamma, the longest distance in air. And beta, as always, in the middle. So I hope that helps. So now, just a little bit of a wrapping up. So I just want to thank everybody. So thank everyone for joining us tonight. We hope you found this session really, really valuable for your exam tomorrow. Before we sign off, don't forget to join our next revision session. So you can see that on the timetable that should be posted in the chat now. So there's also your feedback will help us make even better revision sessions. So please, there should be a little form that's pinned in chat. Please complete that form. Tell them how much you loved my session. Tell everybody how much you loved it. Don't forget to subscribe. So there's a little subscribe button at the bottom, and make sure you click that notification button as well so you don't miss out on any future sessions that we're doing. Thanks once again for being part of that revision session. So thank you for everyone for coming this evening. Remember, you've got this, so you're going to do so well tomorrow. I'm really, really wishing you all the best in your exams. Stay focused, stay motivated, and keep striving for success. See you next time. Thank you for joining us. Goodbye.